So we talked about pure bending. Let's kind of look into how this translates into actual beams. So if we have a beam that has a setup like this, it's supported on either end and two forces in the middle, and those forces are uniformly distributed, then what we're going to end up with is a shear diagram that looks like this and a bending diagram that looks like this. So again, in the middle here, we've got a uniform bending moment. And it's going to be a uniform positive bending moment. So in that section there, we're going to have, it is a pure bending moment. So we're going to have a constant radius of curvature there. So the rate of change of the slope is going to be constant. Whereas in this section here, and in this section here, we're going to have it's not going to be a constant radius of curvature. So kind of at this point here, the radius of curvature is actually infinite, because kind of at that point, where the bending moment drops down to zero, there's no curvature going on at all. So it's effectively straight at that point. And then once a bit of bending moment builds up, then the change in the slope starts at zero and then increases linearly. So again, that doesn't mean the slope's positive, but it means it's increasing. So again, the slope this entire way, the slope is negative, but it's still increasing. So it starts out with negative, and it starts getting bigger, and it starts getting bigger, and it starts getting bigger this entire time. And that's because this entire time, the bending moment is positive. So positive bending moment leads to a positive change in the slope as you move along the x-axis. And then again, in this section here, you get to you no longer have a constant rate of curvature, so the change in the slope starts to decrease until it hits zero, and then kind of at this point here it's effectively straight. At this point here it's straight. So again, instantaneously at any particular point we can kind of consider what the radius of curvature would be kind of at that little point. And that leads us to being able to determine that the change, the double derivative of the displacement over x is going to be equal to that amount. So again, that's just based upon the geometry of kind of if we're looking at a little segment zooming in, we can relate the rate of change of the slope to the radius of a cross section, to the radius of curvature at that little point. So things that need to be kept in mind. So anytime you have a bending moment 0, the beam is straight. When you have the bending moment changing from positive to negative, so that'll be an inflection. So for example, if I had a beam that was set up like this, and I applied a moment in the middle, then essentially what that'll do is that'll cause, this portion here is going to want to curve up, this portion here is going to want to curve down. So that'll cause a curvature like that. So if we graph our bending moment diagram, then essentially what that means is that it's going to be positive on this side. Oh, so actually wait, no, sorry. It's positive on this side, and then hits that point, and then drops down to negative. So at that inflection point, that is the point where the moment diagram crosses the x-axis. So anytime you have a change in the bending moment diagram from positive to negative, there's an inflection point. So you can tell that by looking at the beam when you graph if you sketch a little deformation of the beam, how you expect it to change, it should align that inflection point should line up with where it crosses the x-axis there. And then again, when your bending moment's small, the rate of change of the slope is small. When it's large, the rate of change of the slope is large. So, obviously we can, if we have our bending moment diagram, we can integrate it twice to get our displacement. That is, of course, a giant pain in the ass, and we're not going to want to do so every time, especially considering, you're you're far more likely to have little errors build up over time when you do so. So I got pre-calculated solutions based upon what the loading and support situation is. So for example, if we have a cantilever beam with a load at the end, then this gives us our displacement at any point. This gives us our displacement at the end, and this gives us the angle at the end. And if we have a beam that has a point load somewhere in the middle, then again, this gives us our displacement at some point between here and here. This gives us our displacement at some point between here and here. And the displacement at the end and the angle at the end. So on and so forth. So again, there's a few of these. Uniform loading for a cantilever beam across the entire length. Uniform loading for a cantilever beam kind of goes halfway through. A linearly decreasing uniform loading. And then what happens if you just stick a moment at the end? So that's for cantilever beams. We've also got simply supported beams. So what happens if you put a point load in the middle? What happens if you put a point load somewhere other than the middle? What happens if you have a uniform load over the entire length of the thing? What happens if you have a uniform load over part of it? What happens if you have a uniform load over, a linearly increasing uniform load? And then what happens if you just apply a moment at the end? So again, those can tell you what your displacement's going to be. So you can also use the method of superposition in order to figure out what the displacements are going to be overall. So again, if you have a beam that has multiple loads applied to it, then you can figure out what the total displacement is by figuring out, all right, here's the displacement curve that would occur if I just have this point load. That's this one here. And then here's the displacement curve that would occur if I have this uniform distributed load that occurs over half of the segment. That's this here. You'll notice that's a straight line right there. So again, it shouldn't be surprising that in this segment here, there's not going to be any moment generated at that point, so the slope will be constant for that segment. And then just taking this, adding it to that gives us our total deflection based upon this combined loading situation. So we can use these to solve indeterminate problems. So what you're going to need to do is you're going to need to figure out what sort of compatibility condition matches your situation. So that's going to be based upon having known displacements, such as zero displacements at the supports. That's a typical one. Known slopes, such as zero slope at a fixed support. And oftentimes what you want to do is you want to take one of the reactions for the supports and kind of just remove that support, and then add that reaction as an unknown load. So we can treat this entire situation here, this beam here that has this uniformly distributed load with the support in the middle, as if it was a simply supported beam that had a uniformly distributed load over the entire length and some unknown load there. So that is going to cause, the just the distributed load would cause a certain amount of deflection downwards, and the point load upwards in the middle is going to cause a certain amount of deflection upwards. And you can find out the magnitude of that reaction there by figuring out that, hey, the displacement here needs to be 0. So these two things need to be equal in magnitude. Or, taking this and adding it to that needs to be equal to 0. So that'll be a negative displacement, and a positive displacement needs to be equal to 0 in order to get us to where we want to be, in order to allow us to find out what that reaction force is. So based upon that, we would be able to also find out, what our shear diagram looks like, what our moment diagram looks like. From there, what stresses are induced are, and we'd also be able to figure out what the final deflected shape would look like. So that'll probably be, that'll be something like that, probably. But anyways, yeah. So that's that would be how you solve indeterminate problems. So I'll be going over a couple of those shortly.